Let's think about differential equations. This is based on Chapter 9 in Stewart's calculus book, and specifically I'm assuming that you've looked at the first few pages, 9.1, most of that section in Stewart's book. It also starts out of section 3.8, which is a very early to a very basic intro to a very basic differential equation. And so what we're looking at in terms of a model is another model of population growth. It's similar to what the book does in 9.1, but I want to modify it just a little bit. It's pretty similar, but I didn't want to copy exactly what he was doing. It's definitely the same starting point, which is section 3.8. So let's review that very quickly. I have other videos about that, so it's going to be very quick about constant relative growth rate and exponential growth. So let's say we're looking at the population on not Easter Island, but Halloween Island. It's a more fun place. They dress up all the time. And T is the time in years starting from, let's say, now. And Y is the population, let's say, in thousands of people, because the numbers will be simpler if we put the units in thousands of people. So here's the simplest model for population growth. And you can get you pretty far, but not that far, really. The population, well, let's say Y of T, grows at a constant relative growth rate. And that relative growth rate is something I emphasize in my classes. Haven't talked about it in a while since we've been doing integrals and volumes and things, but we want to get back to it. It's not just dy dt, it's the rate of change of the population as a proportion of the population divided by the population. And let's assume that's a constant. For example, whenever I want to put in a number, I'll use 0.01 as an example. So if you move the y over, you get what's called a differential equation. The derivative of our mystery function y is given by some formula, but that formula is not just an explicit function of t. What it's really saying is that there's a relationship between the derivative y prime and the function itself. And this is the simplest differential equation of that form, where you have a y on both sides. Let me make a contrast to anti-differentiation. That's where the mystery function y, the derivative of that, is a specific known function, like, let's say, cosine of 3t plus 7 or something like that. Okay, there we would take the integral, the antiderivative of 3t plus 7, and we have been doing that, 3t. We have been doing that a fair amount lately, taking antiderivatives, using things like substitution. We know at the start of that story, although there's a lot more what we could say about taking antiderivatives. But this is different. This is where you just start with a function of t, it's an explicit function, and you anti-differentiate. Find the mystery function whose derivative is this guy. This is different. This seems harder because now the unknown y, the mystery function that's going to describe the population growth, appears on both sides of the equation. And that's always harder from the start of algebra. We know it's harder when that appears on both sides. The trick is going to be the same thing. Try, at least for the simple kinds of differential equations we're looking at, is to get the y's both on one side somehow. And we'll talk about that as our very last real major topic in the class, separable differential equations. So, but right now I want to talk more about the idea of a differential equation and some of the pictures and the geometry. Okay, so here's what I was just saying. The mystery function y is on both sides up here as opposed to the anti-differentiation story. Now, there are things we can learn from anti-differentiation. It's really tightly connected with this story still. And in particular, if you're going to give me this situation, that does not specify y of t. And think about the population example. If I say that it grows, the relative rate of growth of the population is 0.01 per year, 1% per year. 1% per year. Okay, that's what that means. You can't tell me what the population is unless I tell you the starting value. Okay. Well, so we still need what's called an initial condition. And let's say 1/2, or in other words, 500 people, to be definite. Okay, so what this is called is an initial value problem. That's a differential equation plus an initial condition, often abbreviated IC, and that's called an IVP, initial value problem. That is something that has a unique solution. So y prime equals 1/100th y, y of 0 equals 1/2. That's something we can expect to have a solution. And we know the answer to this guy. If you want to see more about this, you can look at my exponential growth and decay video. Y of t is some constant times e to the kt. We know that that's the kind of thing that has this property of its derivative. And the c in this case is just exactly y of 0. So here's our explicit solution. It's an exponential growth. That's the kind of function that has constant relative growth rate. Okay, so let's see. Oh, it looks pretty reasonable. We start out with 0.5, that's 500 people, and we grow and grow and grow up to almost 4,000 people in 200 years. Okay, that doesn't seem unreasonable, and if we extrapolate back into the past, we would predict that we would have had maybe like 250 people back here, something like that. Now, what about in the far future, though? Let's extrapolate that out 2,000 years. Look at the scale here, okay? Remember, y is in units of thousands of people. We've got this little tiny island, Halloween Island. We're predicting after a long, long time, 1,400 years, that it's going to have 1 billion people on it. And then it keeps on growing and growing and growing. It just gets ridiculously high. So that isn't actually very reasonable. So there's got to be something better here. But before we find a better model, I want to show you a wonderful picture of the data of a differential equation that applies to any differential equation of the type we're going to do, and gives us a wonderful picture of what the differential equation says. It also allows us, if we have a computer, to get a graphical solution very easily. So it's called a slope field, and I've got this nice applet that comes from Rice University, from an old colleague of mine, in fact, John Polking, called D field. That's for direction field, but in the book we call it a slope field. So what I've done is I've entered in y, and there's a tiny little tick mark, prime equals y over 100, independent variable t, and I put in the display window, and I just press graph, and the phase plane it's really a terminology for a more sophisticated idea, but it's really just graph what's called the slope field. Okay, so what does this do? We're going to go into more detail about this in another video perhaps, but at every point, it's a graph of what is this information telling us of the differential equation. Let's go back to here. It's not about the solution so much yet. It's about this differential equation. Y prime equals 1/100th y. It says that if I do have a solution curve for this equation going through one of these points, and I will click in here to make one, the property of that solution curve, which we see is a piece of an exponential in this case, we already knew that, is that if y is, let's say, 2.2, then the slope of this curve at that point should be 2.2. Now that might not look like 2.2, sorry, not 2.2, 2.2 over 100. Aha, okay. That might not look like 2.2 over 100 slope, but if you look here, there's a handy thing that says, oh, a slope 0.1 on this scale, where the t scale has hundreds and this says just 1, 2, 3. Actually, that would be very steep. Okay, so these arrows actually all just recognize or register the y prime for each point. And the property of being a solution to this differential equation is very simply expressed in terms of the arrows. It means just follow the arrows. Follow those arrows. Draw a curve that follows those arrows. This is great. Okay, if you have those arrows plotted, then we can actually by hand rough out a solution. And if you have a computer that follows the arrows in a very accurate and fairly sophisticated way, then you can get all kinds of solutions. Now notice what we've got here. We've got a solution to, it's really a family of solutions to the differential equation. Remember, to get one solution, we actually have to fix an initial value. You have the differential equation, that corresponds to the arrows, and then the initial condition picks out, okay, like y of 0 equals 1/2. Let's actually, I'm going to clear out everything. Y of 0 equals 1/2, it's really this puppy right here. Boom. And that's exactly the thing we have graphed over here. So this is a very nice tool that we'll be using as we explore differential equations. So let's think about making this a little more complicated, though, because really we've just replicated with a little more sophisticated terminology the story of exponential growth. So let's say, suppose we look at Halloween Island, and whoa, that did not work at all. Okay, we look at Halloween Island and we note that at the top, okay, there's only enough food and shelter for around 1,000 people. We find it very implausible that as we get near or above that many people, that we're going to be able to sustain population growth. And so what we want to find is a model where the relative growth rate is going to decrease sharply as y gets near 1. It's very similar to what's called the logistic model. But in the logistic model, we make the very simple assumption that the relative growth rate goes linearly from whatever it was at 0 down to 0 and then goes negative. In other words, it's going to be a decay. People are going to die off or leave the island, let's say. Maybe that's more pleasant. Here, I'm going to let it be a curve, so that, in fact, when the population is 200, 400, 600, we still get a pretty strong relative growth rate. But as it gets towards that 1,000, let's model it as sharply decaying at that point, and even maybe going negative if we get over the carrying capacity of the island. So this is a terminology for this is often called the carrying capacity equals 1,000. Okay. So the function I used here explicitly to model this guy is 1 over 100, so we get the right growth rate when there's very few people, times 1 minus y cubed. When y is 0, I just get 1 over 100. As when y equals 1, this thing is 0. And it's like an upside down cubic, and so it's fairly flat here, not changing too much, and then pretty drastic decrease in the relative growth rate there. Okay. So if the relative growth rate is given by this guy, then what that's at? Well, the formula for relative growth rate is just 1 over y dy dt. So dy dt is now a more complicated thing. It used to be y over 100, and now I'm introducing this other factor. It's going to make the algebra significantly more complicated if we try to solve it, but it's still a meaningful differential equation. And the nice thing is that a lot of what you want to do with differential equations, we don't actually have to focus on the algebra of solving these guys. That's part of the modern viewpoint of differential equations now that we have computers. Let's say the initial condition is still 500 people. Y of 0 is 1/2 in units of 1,000. Let's try this on D field. What's the different picture here? We should get something that accommodates our intuition that this should so let's see, y times 1 minus y cubed over 1,000. This should accommodate this idea that it won't grow so quickly. Okay, now let's see. What do we got? Let me just change this a little bit. I don't think we need maximum y is 5 anymore, but otherwise it's good. Now, where were we? T equals 0, y equals 0.5. Boom. Aha. So now we have something that grows, but as it's growing, it actually isn't concave up anymore, because it starts feeling the bite of getting closer and closer to the carrying capacity. And what we notice is these arrows are getting less and less steep as we get towards the carrying capacity. Let's see if that makes sense with this guy. Remember that if I put in a y that's close to 1, this is close to 0. Or let's actually highlight this guy. This whole quantity is close to 0. That says that my mystery curve should have slope close to 0, and that's indeed what's happening up here, that as y gets closer to 1, all these arrows, no matter when I get there, no matter what the time is when I get there, it flattens out. This is also predicting that if I start out with a population bigger than 1,000 people, bigger than y equals 1, people are either going to die or leave the island because there's not enough room for them. It's also interesting to look at the negatives. Is this weird? Let's see. That's weird. We start with negative 200 people. We quickly go to negative 400 people. That's weird. This is a great example of a mathematical artifact that in our model almost certainly has very little meaning. And that's something to always watch out for. Okay. So this is the kind of thing we're going to be looking at. Some mystery function. Its derivative has some relationship to itself. Okay. Often we're going to have y's and t's over here. I just wanted to make it somewhat simple by not having a t as well as a y. And we may or may not have an initial condition to pin it down. Sometimes we look at the whole thing and we want all these solutions. Sometimes we're specifically interested in just one, like here with initial condition. And then for some of these guys, we'll be lucky enough that we know how to actually do the algebra to find a formula for the solution. To be honest, that's not the major concern. The major concern is to be able to produce this kind of picture and understand this picture, what it means. There's all these different scenarios that fit this same model, but with just different initial conditions of growth and then slower growth and then maxing out, in this case, towards this what would be called an equilibrium.